considered to be sign of stupidity. In many cultures, they're considered to be the signs of wisdom. So, yeah, Scottish, they consider owls to be sign of wisdom. It was a huge owl. I'm not an expert in owls, but yeah, they look intimidating, quite intimidating. All right, so we are live. We will continue our discussion. Nanomaterials. Nanomaterials, we defined some ways how we can categorize them, either by how they are clustered, either by how they are part of the bulk, and then we looked at their classification based on the material type that they're made up of, or some properties that they do. So we'll look at some of the nanomaterials today, mostly are carbon-based, but then we want to get into quantum confinement, the concept of quantum confinement, and how does that relate to 0 dimension, 1 dimension, or 2 dimension nanomaterials, and how do we use that? We'll go through pretty fast because a lot of literature has been published on many of those things. So first, let's start with BuckyBalls. There are many names you will find about them in literature. So there's been lots of push on producing novel nanostructures, and many times we want to build them for in a stable way and trying to get multifunctional activities with them, and want to connect different materials in different way. So this is a very unique nanomaterial, which is 60 carbon atoms making a very close form. They say it's the most compressed and the strongest material in the world. It's stronger than the diamond as well. And there is an interesting history behind carbon 60, BuckyBalls. They're also called Buckminster fullerenes. So fullerenes. So that's another name that we give them. So C60 or BuckyBalls, their spectrum or their features were known from a long time ago. In 1920s, they were looking at, astronomers were looking at wavelengths of light that were coming from astronomical objects. And they were finding that some wavelengths were getting dimmed or getting suppressed. Their emission was not reaching to the Earth from certain stars. So they were seeing missing wavelengths. So, and that was a interesting problem, that what would be those materials that are absorbing those wavelengths before they get to the to Earth, where we are trying to look at them. So this probably about 10 years, within 10, 20 years, we found out, and once we discovered carbon 60 and they did lots of analysis, we have found that there are C60 kind of exactly BuckyBalls in space, which, because now we know in labs, they absorb that same spectrum of wavelengths as was observed by astronomers. So it has, it mesmerized folks for a long time, that what were those things in the outer space that were suppressing. So now we know a lot about them. They are the third major form of pure carbon. They are heat resistant. They have very good electrical conductivity. And they come, lots of modeling has been done to present them, to show them. So you'll find many different ways of how these things are done in experiments, and there are different ways how these are grown in the labs. And the folks who who actually found practically synthesized C60 in the lab, they got Nobel Prize, and there's some interesting history behind. Sir Harry Kroto was a scientist, chemist in UK who was studying these for a long time. And he decided to spend a summer in Houston. There's a university, Rice University, Dr. Smalley and Dr. Curl, they were there. So this was a summer project for them. So he came and they grew graphite in the lab. And so they had a hypothesis that this would be a molecule with hexagonal carbon rings, but this would be different from graphite structure. So they discovered BuckyBalls. So they actually synthesized BuckyBalls. And there's some interesting story about it that they say they got it from the soot, the carbon, the black thing when you burn coals, and you had on the walls on chimneys, the black thing. So that's called soot. So this could be found there. I met Dr. Sir Harry Croto a couple of times. He passed away 5 years ago. A fantastic gentleman. This is my picture with it, so I like to brag about it. So C60 has been used for many, many different application experiments. Now, if you think about it, this is nothing but you take a sheet of carbon and you take 60 carbon atoms and you make a ball out of it. So there is some inherent stress also on those carbons, because the carbon is making some double bonds, some single bonds. So there is an inherent stress on the molecule, but the forces of their binding keeps it intact. And this is just showing comparison when we say the third most compact. So we know diamond, we know graphite, and buckyball is the one of the things which is most compact material and hard material in nature. And here it's color coded, showing yellow bonds are double bonds and red bonds are single bonds. So you can see that there are 6 ring and there is a 5 ring, hexagonal and pentagonal. So the rings alternates. And so the pentagonal, they contain only single bonds, and double bonds have shorter lengths. So they are the ones which create the pentagonal rings. All right. So,
sir, question.
Yeah, go ahead.
How big can buckyballs get? I mean, could there be a physically big buckyball?
It's a powder.
It's a powder, so no, they get a ball type.
No, it's few nanometers.
Oh.
It's few nanometers. It's a nanomaterial. We're talking about materials which we cannot hold, but you get enough of them, you get a powder. And you can suspend that powder in that suspension, then you can know concentration, then you can know how many would be there in a given volume of a liquid. Yeah, so the materials that we are talking today is nanomaterial. You cannot hold them, they're too small. But we do reactions with them, we characterize them, we know their properties, we know their bond structures. So, and because of their special structure, they show very distinctly different physical behavior, right? So for example, if you look at reaction, so C60, or there's another form of buckyball, which is C70, they can, we can do additional reactions. We can have many of them joined together using monomers, which can make a polymerization kind of matrix. So you can have a slab of buckyballs together. So that would become a polymer. You can replace some bonds. You can do substitution with other functional groups. Yeah, question.
Sir, how we quantify fluorines or functionalized fluorines in water, sir? Like it's a powder, sir. So how we can functionalize or detect in water, sir?
How can we? Can you say it again? How can we do what? Functionalize water?
Functionalize fluorines in water, sir.
How can we suspend buckyballs in water, right?
Yeah.
They don't dissolve, so they will make a suspension, right? So there are SOPs for that. There are recipes for that, that which solvent would be, which solution they would be able to stay suspended. They may get oxidized. So there are so many reactions. It's very versatile that you can add different functional groups to it. You can change its property by adding, there's a whole range of, some of them are given. You can put epoxide, fullerenize. You can eliminate some carbons and it can remove some carbons from the structure. So there's a whole bunch. And if you want to look at specific reaction or how it is done, yeah, you have to look up the literature for that. But a whole bunch of recipes are available for various reactions that we can do with graphene. All right, so that's, now we call, sorry, I said graphene, I should say BuckyBall. So BuckyBall, we call it a zero-dimensional material, right? Zero dimension. It has, it would be like you put a dot on a paper. So when you put a dot, we call those kinds zero-dimensional, right? Although they have some weight, but the idea is in X, Y, Z, they're all the same. So it's a circular thing and very small, so we consider them zero-dimensional materials. Now, when you have a sheet of graphene, or if you take and stretch it, add many more, we get carbon nanotubes. So carbon nanotubes is taking a graphene sheet. So, okay, so graphite is many graphene sheets stick together. If you can take one sheet off of it, and we'll talk about that also today, about graphene, and we find a way to roll it, make a cylinder out of it, and that is what we call as carbon nanotubes. Now, carbon nanotubes are again very special material. They're very strong. They're stronger than steel, 100 times stronger than steel, while they have 1/6 of the weight of steel. Now again, this is nanomaterial. If you would buy CNTs, they would come in a powdery form. And then we can suspend them in suitable solvent. And we have to follow their SOPs. We know exactly what chemical needs to be put in and how we can manipulate or deal with CNTs. They give excellent electrical conductivity. When you talk about superconductive materials, that would be example of that. But then where do we use it in electrical devices? That's a big question mark, because they're so small, it's hard to put one CNT in a circuit and put precisely where we want it to go.
Yes,
But
sir.
a bunch of them.
Yeah. Can we make something of carbon nanotubes at a macro scale?
We can see them. That's the answer right here. This is a transmission electron scope image, and they are used in all these things. Can you see the slide?
Yes.
They're used in all these things already. So we don't use CNTs completely. CNTs would be very expensive if you want to make the whole structure, maybe the racket. So if you play tennis, squash, any of the games we play with rackets, they are light, very light. When I was young, I'm still young, yeah, I was younger, they were very heavy. So we would have rackets. The racket itself was, I don't know, 5 pounds, 2.5 kilo, 2.5 kilos. But now you have rackets which are like barely a pound, maybe half a kilo, right? So we are using composite materials with carbon nanomaterials in that, which give them the strength and which are lighter. We'll come back to these applications. But you have to understand that when we talk about carbon nanotubes, and there is a KPR coming up also on that. So you'll see an application on biosensing. You can throw a bunch of those. So we can know in solution the concentration, and then we can have some control over when we use a solution to place them and we dry up. We can have some control or some idea of what would be the density of CNTs in a circuit. But then there is problem that would we have same number between two, maybe source and drain of a transistor? So CNTs, although they have these amazing properties, we still are looking for reproducible ways of using them in certain. Let me look at chat. So how can a material? Andrea's question. Amjad, that's the beauty. That's the nanomaterials. That's where classical way of looking at things breaks down, and we have to adhere to equations, what we call quantum mechanics. So that's exactly the very well put question. The question is, how can a material be heat resistant but electrical conductor at the same time, right? So you are coming from a classical point of view of modeling and equations that we know. And this is exactly why these are special, because the classical equations or models break down, and we have to come up with new equations and new models to understand these. That's what is called quantum confinement or quantum mechanics. All right. So we can grow them. There are, again, many recipes known how we can grow carbon nanotubes. There were it used to be a novelty, but now if you have a decent furnace in the lab and you can create vacuum, we can easily grow carbon nanotubes. And we know two types of carbon nanotubes. There are many more properties related to CNT. There is the chirality of those. There is the angle of the carbon links going from one to the other one. So there are many more ways how we define, but generally we get two types of CNTs, metallic and semiconducting carbon nanotubes. Metallic ones are single wall nanotubes, as it says SWT. So they're metallic. And the multi-wall nanotubes, we write them MWNT. They are generally semiconducting. So, which means that they show a voltage gap before they would start showing the ohmic relation between voltage and current. So we get two types. We're already using them in many applications. We are using them as composite materials in ceramic, metals, polymers. We are using them to do coatings, paints on the surfaces. We are using them as tips of the AFM or STMs, right? So instead of, remember we had the sharp tip, so they're being used as one carbon nanotube as the tip. And you can imagine we are really getting to atomic scale with those kind of tips, but those tips are expensive. Cool. We are using them to do biosensing, lab on chip. We are doing them to coat them with specific molecules and put them in living systems so they can deliver drugs. So we are using them to sense toxic chemicals, for example, when you say chemical sensors. They are being used in water filtration as filters. Of course, again, in a composite structure. When you say composite, which means that there is a large amount of the base material and we add them to that and we mix it or we cure it or whatever way we do. So that's when we are using them as composites. So then the original material, the bare original or simply original would versus the nanotube mixed material would show very different properties. Right. So in electronics, we are already making field emission displays. So we have become good at finding a concentration and placing them. But still, there are challenges on the placement of CNTs and finding the exact amount of the conduction between two. So we have range of conduction that we can get, but still, when you say single electron transistor or nailing it down to specific resistance or specific conductivity, so there's still lots of work going on with that. So energy, they are being used in membranes for hydrogen storage, for solar cell, where we have to, when you get a photon, you get an electron in hole form, so you want to sweep it out before they recombine. So fuel cells, again, where you have to separate the anode and cathode. So we use them for increasing either the cathode or anode capacity, because when the surface is rough with CNTs, you have dramatically increased effective surface area, which means they can be charged to a very higher extent. So that batteries can have huge capacity, which means they can keep on going for longer time. So, of course, the superconductive material as well, because of their conductive properties. Imran, you have a question, or you just left your hand up?
Left my hand up.
Lower your, yeah, sorry,
Sir?
imagine that. Yes, sir.
Sir, is a fluorine a good conductor? Can we use it for electricity, sir?
Say it again. What is more conductor?
Sir, is a fluorine is a good conductor? Can we use as a electricity, sir?
Electricity.
Yeah.
You mean carbon nanotubes used as electricity?
Like, sir, some people said that, sir, its structure resemble to that a graphic. This is the conductor is a good electricity for that. We can use fluorines as a conductor, sir.
I'm not getting the question. Fluorines as conductor?
Yeah.
What is fluorines?
So I guess he's referring to BuckyBall. Are you?
Yeah.
Fullerenes, BuckyBalls. So it's saying, what should we do with fullerenes? Use them as conductors?
Yeah.
Yeah, so if you make a composite material, they can increase the conductivity. So you can increase the conductivity of a conductor. You can make them better, which would mean less heat, less thermal loss, right? So when something is a better conductor, which means they have less resistance, right? Less resistance means less energy lost as heat.
Sir, but someone said that, sir, BuckyBall do not have a layered structure, sir. So we did not use it as a good conductor, sir. Is it correct, sir?
I have no idea what's the question and what is ladder structure you're saying?
Layered structure or layered structure, yeah.
I have no idea about that. Right? So you'll find many applications. You'll find people have tried to do put them in conductors, make composite materials. So there are various applications that you'll find. If somebody has that paper, yeah, so maybe. So we'll have to look at that paper and see what is their data and what are their claims, right? There are 1,000 papers published every day, Shaji. You can't expect me to know if that special use case where they have said something about lack of usage of BuckyBalls. All right, let's stay in the introductory side of nanomaterials. All right, when I say introductory is what we have here. We have CNTs used in biomedical applications. So on the last slide, I don't want to go into other applications. We'll stay within the scope of this course, where there have been many high-profile publications that have come out, which have shown CNTs can easily go through barriers. They can result into pathological changes inside the body. They can be toxic. They can pass through easily. So there have been many conflicting reports. So a lot of data is out there, but there are people who feel it's game changer. There are people who believe that then more work needs to be done. But there is few applications which I'm sharing which have been done to show inflammation, to show immunity problems. There've been some work where they had actually put these things in carbon nanotubes in animals, and they have studied them or used them to do localized heating, for example, or to use them as a Trojan horse type of thing and deliver some drug molecule into those cells and showing that they can reduce the cell growth, especially if the cells are disease cells, cancer cells, for example. So many applications or lots of work from biomedical point of view has been done on this, right? So that's where we can look at some particular application or use case and then learn from those that what are results on specific conditions. But I know that a lot of CNT or nanomaterials are used in, for example, coatings that are hydrophobic, which means if they are in air or in the water, for example, Air Force or Navy, so those surfaces become hydrophobic, which means the water does not corrode or the air resistance is less, which would mean less friction, right? So which means you have to burn less fuel and you can have more range. There have been those coatings which have been used on armament, for example. There have been these materials which have been used in the armament itself, mixed with the gunpowder or mixed with those rocket fuels to have more energy so they can move faster and move much faster. So there are applications in those areas. Now, why those areas matter? Because people are exposed to that. People who work in these things and people who handle. So that brings in the biomedical applications on those special fields as well, right? So industry may not be using without doing biomedical testing on the exposure related to these nanomaterials. All right, so carbon nanotubes are one-dimensional, right? We take them one-dimensional because their width is almost negligible compared to their length, right? So same case would be for nanowires. So some of you are doing KPRs or have read nanowires. So nanowires are also taken as one-dimensional because the diameter or width is almost negligible with respect to the length of those things. Now, two-dimensional material, graphene is the first real two-dimensional material ever discovered. Now, before we look at that, you have to know that the concept of graphene have been around for a long time. It's not something that came about recently, but yes, in 2004, they found a simple way of actually experimentally getting graphene. So when you get them, so now we got graphene and now we could test all those theories that were there from as far as 1946, right? So there were scientists who had this idea of a one-dimensional carbon layer, right? And in 1984, this form and shape was shown theoretically that this would be how graphite is made. Now, graphite is something which is an everyday material, right? So like here on the top right-hand side, this is graphite. This is where your pencils are made, right? We'll come back to this. So now, what was special? So this team from Manchester, they could experimentally get graphene. When you say graphene, that means one layer of carbon sheet. Now, this also has interesting properties. It doesn't have any voltage gap. Voltage gap on devices, we call it voltage gap, which means it's superconductor. It's strongest, it is lightest, and most conductive material known to mankind. Natural occurring material that's known to mankind. Now, graphite is millions of layers, billions of layers. Taking one layer out of that graphite is the big question mark, which was solved by Geim and Novoselov in 2004. some people still believe that some others had already got graphene made, but yeah, there is some debate. But anyways, they got the Nobel Prize for that. And they have done lots of experimentation. Many people have done experimentation on that, where they have measured the strength, which shows that it's 150 times stronger than steel of the same weight. It's when you get a graphene into, again, you would get it like a powdery form. So if you make a small bead out of it, it would be pliable. And if you stretch it, it can stretch 120% of its length elastically, which means it can regain its original size. And ultimate tensile strength compared to, it's in gigapascals compared to megapascal for structural steel that we use to make our skyscrapers, our tall buildings. So that's in megapascals. This is in gigapascals. So it's very light, even 1,000 times lighter than paper. Again, question is, where do we get it? So the companies who sell it, so they would sell you in a powdery form. There'll be small pieces of graphene. So then you have to follow SOPs and follow recipes to get single layer to whatever experimentation we'll be doing. All right, so Hamza, so then we don't have graphene of 2 meter long that we start stretching, but we have small pieces and we do hold one edge and we stretch the other edge, again using ways maybe AFM or STM, where you can hold it down and stretch it. So that's where then you see that how much force would you need to stretch it. If it can withstand that kind of force, that would tell you that this is the strongest material. But if you apply same force, if according to this, 150 times less force would be able to break steel apart or break a steel particle into small parts, small fragments, but not graphene because it has higher elasticity, right? So when you say tensile strength, so there are experiments where all these things have been taken on graphene to get these properties about it. All right, so yes, ma'am.
So when all these nanomaterials are being compared for their conductivity and for their strength with steel and so we have been using steel and wires for so long that whenever I imagine if it's stronger than steel, so I imagine a big wire or a big tube coming out.
Right.
So yeah, and so that's I think the question came up, like how can it be stronger than steel? So we'll use steel materials, steel wires, and steel as like even our gates are steel. Or so like we talked them about in a nanoscale, we compared with a very little small steel and say like so
right.
we don't have.
So you have to do apple to apple. So you have to get a smaller sample of one thing to compare to the small sample of the other thing, right? So when you talk about the properties of materials, yeah, there are specific experiments that are done to find ductility, strengths, tensile strengths of one material. And you do the same thing to find the same property of the other material, right? So I've got the bullet points from literature where the numbers are given. But yes, there are very specific experimental protocols to compare one thing to the other, right? And when you get, for example, you get structural steel. So there are tests that are done and they provide you a certificate of those tests that this has been done to show withstand this force or that force. Those numbers are compared when you do that experiment on a, now nanomaterial, you wouldn't have the same size, but you have smaller size. Now, when you do the comparison, you are doing comparison with the unit dimensions with unit dimensions, right? So we have to translate those numbers from big P's to what you call normalizing. You have to normalize the data to compare apples to apples. You cannot compare 1 meter of steel with 20 nanometer of graphene. But yes, so when you get the data for that, you have to find how much would be to, for example, I'm just throwing a number. What would be the 20 nanometer contribution towards 20 nanometer of graphene? And these are not done in a similar way, but there are other tools that are used. For example, AFM. AFM can apply forces. With STM, you can drag things and you can push things. We know the unfolding force of a protein because we bind it and then we stretch it. And so we know exactly how much force we have to apply to unfold a protein. So those forces for those nanomaterials there are ways of how to measure those. And then they are compared with the forces of other materials, right? So that can be a good KPR topic, by the way, of who measured the force or tensile strength of graphene.
Yes, sir.
Right? So it's completely impermeable to gas. What does impermeable mean? Permeable means they can go through. Impermeable, gas cannot go through. Right? It can, so there's known that graphene oxide can attract radioactive material. You know, I don't know if you remember Fukushima reactor meltdown, which happened in Japan. So they say that they use graphene oxide there to attract and capture the radioactive materials, right? But the data is debated about that also, that if it was effective or not. But yes, so they tried to do that, and they made a claim that helped them reduce the effect on the people and the growth of the radioactive radiation from that disaster. All right, so now, why don't we have mass scale graphene features or graphene based fixture? It's expensive to make. When you make, and this is, there are many ways now known, so, but this was the process that the Manchester team used. So they took a Scotch tape, they put the Scotch tape on the graphite block, they took it away. So many layers of graphene came on that, right? But you want one layer. So then they put another Scotch tape, and then they removed 2 Scotch tapes. So some went on the other side and some layers left on the other side. So then they take a new Scotch tape, they put it there. So they kept on removing Scotch tape until they got one layer of, until they got the graphene, right? Until they got the whole graphite removed and one layer left behind. So if you read that paper, you'll be amazed that this was such a low tech, but it required lots of hard work. So it could take 20 times to 100 times sometimes to get to that graphene layer. So once you got the graphene, that opened up the doors to do the experimentation and to find all these properties that I have shared with you. So now here I have talked about quantum dots. We'll talk about quantum dots just a little bit down, but just to give you an idea that if we can find a better way, right now we have at $1 million a kilo for the price of that much material. And if we can do something, we can bring it down to $100 a ton. But that's, again, an area of constant discovery that how can we find easier, cheaper, and reliable ways to create things at that scale. Yeah, graphene has the ability to transmit to 98%, of which means that it's transparent for light. It's fully transparent for light. All right, another question. Seems Scotch's bonding is stronger than chemical bonding of carbon and graphite. Exactly. Now you have to understand, when you look at this one layer, These carbon atoms are in hexagonal connection with each other. The layer on top, those carbon and the carbons below do not have covalent bonds between them. They have pi bonds, which are much weaker. So that's the bond that we have to break to remove one layer from the other layer. So the force or the stickiness is much stronger to remove those bonds. And this is another interesting thing. So when you do that Scotch tape, we would always cut them across the length of the graphene, not it wouldn't like break the graphene structure apart, because carbon to carbon in the graphene is very strong. The gum, or what's the word, not the gum, the glue of the Scotch tape is much stronger to break the pi bonds between two layers, like it is shown here on the right hand side. So no, the carbon, each carbon in the graphene is fully bound with three others. So there's no instability in graphene, the carbon which belongs to one layer. So pi bonds are between one carbon to other carbon, which are much weaker bonds. So that's the only known 2D material that we know up to this day. So Scotch tape, yeah, so but that's where that pi bond is much weaker. Okay, now if you have the carbon, real structure of the carbon, that's not in 2D. That's has a kind of a hexagon, not hexagon, that's kind of a pyramid kind of structure, right? But this is, we are talking about graphene, which is a 2D structure. Yeah, I know exactly, Hamza. That's the beauty of graphene, that we have carbon in a plane structure, and from graphene to graphene in graphite are pi bonds. Now, Scotch tape is a tedious process. There are many processes that have come out, many processes. I'm just sharing one, which is called exfoliation. So the idea is we create first graphene oxide, and then we reduce it. So we can do exfoliation is the process where we break apart bonds. So it's like, we do exfoliation cream to get things out from our skin. So it's a similar process where we can break the bonds between the carbon, and we get graphene oxide, and then we reduce it, we get into graphene. So there, just one example, there are many more ways of now how graphene is made, right? So in energy applications, it's being used for supercapacitors and battery construction. So this is again where we can have now many layers of the in a supercapacitor, we need to have insulator, right? We need to have dielectric material. So you can have many more layers of dielectric sandwiched between graphene. So, and this is an example of lithium-ion battery, which is the biggest segment in the energy storage, right? So this is where they're using graphene as a material which can have much more charge stored, and which is charge in this case is we have to get ions separated, and of course during the operation then ions go back cathode and anode, and we get battery discharge. Another application where they have showed that you can make, this is just they have used a CD to show the size scale of how big are these. And what they've done is they can, I think I was reading, they can charge it for 1 hour and the LEDs can stay on for 12 hours. So with one chip, which is shown here, that can 2-minute charge, sorry, for around 12 hours, 2-minute charge can keep it on for 12 hours. So that's some application in the energy storage also. Rick Kainer is a professor at UCLA, so his lab is doing a lot of work on this. They are in the optical devices, flexible electronics. Now again, it's malleable, it's flexible, so they are using it in many applications related to organic LEDs. But there are challenges with that. It's a hydrophobic material. There are application issues with water, right? Application issues with biosensing. So you have to create an oxide and then it becomes hydrophilic. There's no bandwidth, which means it will continuously keep on conducting. Unlike transistor, where we need control of a transistor, where we want to use the third terminal to control the conductivity. Here, we don't have control over that. Very expensive, hard to manufacture. Some places, some publications, people have not been able to replicate. That's been another challenge, that specific conditions in a lab, ambient, moisture, temperature, I do it and I publish result and you try to do it and you cannot replicate because the material is so sensitive to all those conditions that it becomes an issue to replicate the results.
Sir, question.
Yes.
Are there any current uses of graphene?
Who?
Are there any are there any these are just current or just theoretical uses?
No, these are devices I'm showing you, which is using graphene. Can you see my slides?
Yes.
All right. So these are just two examples. There are many, many more examples. You can look up any search engine, graphene in devices. Yeah, it's used in devices. All right. All right. Oh man, you are yawning. You are ready to go back to sleep, right?
No. So in the medical, you said there also has uses in medicine. So about toxicity.
So that was about carbon nanotubes. That was a while ago.
No, but how about graphene? Can that be used in medically?
So when we talk about the application, yes, there are biomedical application, again, for sensing, for putting on functional materials to get a smaller amount of target molecules that we want to sense. So yeah, so graphene has also been used for biomedical applications.
And what about toxicity of graphene?
So the toxicity, so graphene, I don't know if they have used it to put inside living things or not.
Mm-hmm. Yeah.
Right? Because much more interest in graphene is because of its electrical properties, that it is a superconducting material. It's a hydrophobic material, right? Hydrophobic means it doesn't like water. So my understanding is that if it doesn't like water, then you probably wouldn't want to put it in a living system because that's all composed of water. So it may not be very effective in creating a good nanobio interface. But yeah, we can look up. I'm not sure. We can definitely, there must be some work on that. I haven't looked about that. All right.